All right, let's draw our free body diagrams. Again, these are critically important for us to do this next unit. So, all right, so this object lies motionless on a surface. So we're on this surface, so we're going to assume we're on the Earth. So we've got this mg, or gravity, that pulls straight down. Then we've also got this force normal that pushes straight up. Okay, what's perpendicular to the surface. And that's it. There's nobody pushing it, nobody pulling it. That's really about it. All right, next, number 2. So we got this object sliding at a constant speed along a smooth, frictionless surface. So once again, you've got mg straight down. There's a surface, so we go perpendicular to that surface. That is a normal. And no one's pushing it. It is frictionless, so I don't have to worry about friction. And that is it. It's a constant speed. Therefore, forces are balanced. Next, number 3. So, object slows down due to friction. Just like before, mg, or the weight, you've got your force normal. I'll put Fn this time. It slows down due to friction. So, the object is moving to the right. Therefore, friction must move to the left. I'll label it F sub F. There it is. So this is an unbalanced force. This is the first one we've experienced where there's an unbalanced force. And I think we can see that, right? Like up and down, we've got a balanced force. But left and right, you've got one to the left, but nothing to the right. So there's our unbalanced force. So an object slides on a smooth incline. So just like before we did in class, you've got this mg that pulls straight down. You've got this force normal that's perpendicular to the surface. Now it says it slides. It doesn't tell us that it's sliding at a constant speed or not. But what I'm going to do is I'm going to look at these little lines. These clever little lines I've got. Looks like as time goes on, right? It looks like it's getting faster and faster and faster. See, remember this one up here? These are evenly spaced. Therefore, it was constant speed. So I'm just going to leave it like this. So the other clue here they give me here is smooth. Usually when you see smooth, usually that means frictionless. So this is all I'm going to do. Next, we've got friction on an incline prevents sliding. You've got mg that goes straight down. You got Fn that's perpendicular to the surface. And now we do have friction. It prevents it from sliding down the ramp. So friction has to go back up the ramp. All right, next, we've got an object suspended from the ceiling. There's our object. You've got mg that goes straight down. And you've got this tension force, I'll call it T, that follows the rope and opposes that motion there. Skylar just came into the room. Skylar would like to say hi. Skylar?
Hi.
Want to draw a quick picture?
Okay.
Okay, Skylar's going to draw a quick picture. You have to narrate the picture, though.
Okay.
Okay, there you go. There's your colors. There's blue and red, black.
Okay, I'm gonna draw a picture of a cat.
Looks like a rabbit. Oh, that's nice. Oh, that's outstanding. He needs a little cottontail. Oh no, it's a rabbit, it's a cat, not a rabbit, that's right.
Okay, now we draw a tree. A cat near a tree. Okay, I'm gonna do this a different color.
Okay.
There.
Very nice. Oh, that's good detail. What's the cat's name?
Pom Pom.
Pom Pom? Is it one word or two?
2 words.
2 words, Pom Pom? Is it hyphenated?
What does hyphenated mean?
Is there a little line right here?
Yes.
Sure, okay. We'll keep Pom Pom. Alright, sound good?
Yeah.
Okay, back to physics.
Bye-bye.
Alright. Let's keep going. All right, now we've got number 7. We've got an object suspended from the ceiling. So once again, this object is not accelerating, so we've got, let me make that a little straighter. So I got this mg that goes straight down, and then I've got these 2 different tensions. So I have one here, and I have one here, and I should label them something different because in this case they will be the same, but other cases they may not be. So you can call it TL for left and TR for right, or A and B. I just called it 1 and 2 just because I felt like it. All right, next. This guy here. Once again, you've got mg that goes straight down. You've got this tension here. We'll call this TR for T right. And then I got this one up here, and I'll call this, I don't know, I guess TL because I did that. Not sure it's the best choice, but why not? Let's do that. TL and TR. All right, next, we've got this one down here. Number 9, we've got mg. You've got a normal force that's perpendicular to the surface here. Then you've got a tension force there. Now they don't mention friction. If you want to put friction in, friction would go up the ramp in this case. They don't mention it, so I'm just gonna leave it out. Why complicate things we don't have to? All right, next, number 10. This one's interesting because you got mg down, then you've got this, I don't know, you got one normal here. I'm going to call it, we'll call it N1 maybe. And then there's this other normal force here, and I'll just call this N2. So there are 2 normals, so we should label them something different. All right, let's keep moving. All right, let's go on to number 11. So now some of these questions on this next page are a little ambiguous, but they're ambiguous on purpose so we can have some discussions about them. So I'll do it this way, and then there's other ways we can do it, but and we'll talk about that when I get back to class. So this one says there's an object pulled by a parallel force, a force parallel to the surface. Surface is rough or has friction. So once again, mg, straight down. You've got a normal force that's perpendicular to the surface. Now, you've got this other force here. We'll just call it F. Now, we do have to include friction. Now, this does not say that it's an equilibrium. Does not say that it's not an equilibrium, so we can just make that determination. So I'll just say that it's moving at a constant speed. So what that means for my drawing is this force I had moving to the right should be about the same length as this force moving to the left. So that just means my thing is in equilibrium. So if you had your force a little shorter, that'll be fine. But it should not be bigger. This frictional force should not be bigger than the applied force. So, like I said, this is applied force. I just call it F. If you call it FA, that would be okay too. I'll just call it F.
Hi, Daddy.
Hey, buddy.
I have some toys in here.
You have some toys?
Just for me. Do you see?
I do see. They're outstanding. Do you want to draw a picture for everybody?
Yeah.
Okay.
What can I draw?
I don't know. What do you want to draw? You can draw anything you want to draw.
I choose blue.
There's blue. What are you drawing?
Nothing.
You're drawing nothing? You're just
I'm
coloring?
drawing sky.
Oh, you're drawing the sky? What else are you going to put in the sky? Can you draw a bird in the sky?
No birds.
No birds in the sky? How about a cloud?
No.
How about the sun?
No.
No? This is the blue sky day, huh? Do you want to put yourself in there too? Here, do this.
No.
How about this? Go a little faster. Is that better? Okay. That is blue sky. Alright. Are you done drawing the sky?
Okay.
Okay. Can you put something else in your picture or anything else? Done? Okay, awesome.
I can do some more blue.
No, I think that's good enough. Can you say goodbye to everybody?
Bye.
Say see you later.
See you later.
Okay. Alright.
It's just for me.
That is just for you. Okay. See you later, buddy. Okay. Good work. Alright, let's go back. Where was I? Alright, we're at number 12. We got this object pulled by a force at an angle to the surface. The surface is rough. Like we said, that means there is friction. We've got mg that's straight down. You've got this. Now this time they did label it just F, so let's make sure put that F. So then we've got this normal force here. Now remember I made this one a little shorter. I made this one just a little shorter than this one because there is a component here that goes up. And then we've got a frictional force here. And that looks good. All right, next. So people have a hard time with this one, but let's just remember, I want the forces acting on this block, okay? I just want the forces acting on this. Well, I should have my son's color that in. He would have done a good job. He likes blue. So we've got mg that goes straight down, okay? Then we've got this tension that pulls straight up. So I will keep these generally the same size. Do my best to do so because it does say constant speed. Now notice I did not call this force F. This force is pulling down on the rope. The pulley here, the rope is pulling on this. So indirectly this F pulls this, but the tension is just the force that pulls that. All right, next we got a pretty interesting one. All right, this next one's pretty interesting. Here's how I envision this. So here's our balloon, right? So we've got our little balloon like this, right? We've got our thing here, we got our balloon. So I kind of picture it, it says it's being held down. So I kind of envision like it being kind of tethered down. So I'm going to use it like a rope to hold it down. So if I've got this, the balloon, right? I'll say that there is an mg that pulls it down. I'll say that there is a, I don't know, let's call it a lift. I'll call it a lift force that pushes it up, but I'm also going to have to put this down here, and I'll put this as like a tension that holds it down. And I'm not sure I did a good enough job here, so this force up here should be matched by these forces down here. All right, next we got this object falling, no air resistance. So if there is no air resistance, all we've got is just mg. That's all there is. Next, we got something falling at a constant terminal velocity. So we've got mg that pulls it straight down. And what terminal velocity is, it's like this this air resistance that pushes it up, right? So think about when you're in your car, right? If you have the window open, if you have your hand out the window when the car is not moving, you don't really feel any air. But the faster you move, the more air there is. So the same thing happens when this box falls. When this box falls, the faster and faster it goes, the more and more air starts to push back on it. And at some point, this air resistance matches this gravity. And when that happens, the box no longer accelerates. We call that terminal velocity. So these should be about the same length. All right, almost done. So I got this ball rising in a parabolic trajectory. So we just got mg. That's all there is. It's in the air at some point. I mean, somebody kicked it or threw it or punched it or whatever, but all in the air right now, the only thing acting on it is gravity. So next we got a rocket accelerating upward. So I do have mg that pulls it down, but then I've got this like let's call it thrust. And it is accelerating upwards, so I should keep this bigger than that. All right, next we got a skier accelerating down a slope. So we've got mg that goes straight down. There is a normal force perpendicular to the surface. Then there is, we'll call it F, air, and there's F for F friction. So if I did this right, I'm not sure if I did it super accurately, but this X component of gravity here should be bigger than these right here. And I think it's pretty close enough where I think I'll be okay. Okay. All right, lastly, we've got these two guys here. Now, they want to do each block separately. So I'm going to do each block separately, then I'm going to do them both together. So if we do the blue one first, right, we've got, I'll call this one M, and I'll call this one big M. So I'll have a little m times g. We've got a force normal there, and I'll call that Fn1. And then I've also got this, we'll call this T1 here. So we'll call that T1. And they do say there's friction, so I do have to apply a frictional force here. Okay, and these forces should be balanced. All right, next, I've got, I'll make this one red to make it a little, just to make it different. So here's this block. So I've got, I'll call it big mg, and I'll call it Fn2. And let's just call this, I guess we'll call that T2, we'll call that T1. So let's call this T2. Then we've got T1, and there's a frictional force. So if I did this okay, I should have this T2 the same size as these right here, because it did say it's moving at a constant velocity. All right, and like I said, I'm going to draw each of the, I'm going to draw this as one block then too. So what I can do is I can define my system as this, okay? If I define my system as that whole thing, I've got m plus m times g. I've got this this force normal here. Let's call it Fn, and then I just got this, like all the T2, might as well just be consistent, and I'll call that T2. And there is a frictional force here I should include as well. And they should be about the same size. And there we go, there we have it. So what I'd like you guys to do now is, I'd like you to write an equation in the x and y directions for the diagrams that are not accelerating. Okay, so only do the ones that are not accelerating. So actually, just do these. You don't need to do the second page equations. Let's just do the ones here. So I want you to write equations for 1, 2, 5, 6, 7, 8, 9, 10. So those are the ones that are not accelerating on that first page. So write equations. So do the same thing. So F net in the x and F net in the y. Okay, so all of these should all equal 0. Okay, so do each of these do the x and y for each of those numbers. We'll go over those on Thursday, and then we will start Newton's second law. All right, have a great day.